Okay, so before we get started looking at Newton's second law and how we can use it, there's just some advice about how to actually use videos like this. So for each question that I look at, I'm going to show you the question first without the solution, and it's critical that you have a go on your own answering the question. So once you see the question, pause the video, have a go on your own, and then watch the worked solutions, so then you can actually really get some useful understanding out of this video. So rule number 2, see rule 1. So most people will ignore that advice to start off with. So it's really, really important that you attempt these questions and try to use what you know to answer them. So what this will do is it will prime your brain to put this new information in with your current understanding, which is what you want. If you don't think you have the right understanding of stuff, that means you haven't got some of the basics on this topic, like how to calculate acceleration or those kind of things. So that's useful to know as well. And then once you've seen a worked solution and you've seen the stages, again, it's important to pause this video and ask yourself why each stage of the calculation was done, because that is really critical in terms of developing your understanding. You need to know why each stage was done so that you'd be able to do it on your own. Okay, so let's get started. So the first question we're going to look at is, we've got the first section of the graph and I've labeled it 1 so I can talk about essentially the relevant part. And what I'd like to do is calculate the acceleration of that section of the graph. So pause the video and have a crack at that now. Okay, so let's have a look at how we would do this. So first of all, the piece of factual knowledge that you need to answer this question is that acceleration is the gradient of a speed versus time graph. You just have to know that or you can't go anywhere with this question. The next piece of information you need to know is to calculate gradient, you need to do change in whatever's on the y-axis divided by change in whatever's on the x-axis. Those are the two pieces of knowledge that you need, and then it's just about executing that knowledge. So you can see at the end of the straight line, it's at 6 on the y-axis and 3 on the x, so that's why that comes first in the calculation, because we want the final y and the final x, and they both start at 0, 0, so we subtract 0, 0. So we've essentially got 6 divided by 3, which gives us an acceleration or a gradient of 2 meters per second squared. And you will see me write meters per second like this a lot, ms minus 2, because it's easier on a computer, but this is the same as doing meters per second squared. So that's exactly the same, but that's the way I write it on a computer because it's easier. Okay, so again, next question. We've got the acceleration, we've got the resultant force, 10 newtons, and it wants us to calculate the mass of the object. So again, pause the video and have a crack at this and restart it when you're ready. Okay, so let's have a look at this one too. So first off, if we want to link force, acceleration, and mass, we're looking at this version of Newton's second law. And if we want to calculate the mass, we need to make the mass the subject. So currently mass is multiplied by acceleration. So I've divided both sides of the equation by acceleration to get mass by itself. Plug the numbers in. So we got acceleration from the last question. We've now got the force, and we can therefore get the mass of the object. And if it comes out of an equation, it's going to be measured in kilograms. That's the standard unit of mass. Okay, so those are the two calculations. Next, we'll have a look at something else. So we're still using the same graph that we had before, but we're just going to do some describing and explaining with it. So first off, we've got, if the resultant force was doubled to 20 newtons, explain how the acceleration would change using the equation F equals ma. So again, on your own piece of paper, and it is important you try and write this down and get this done properly, explain what you think would happen to the acceleration, and then you can compare it to my solution when you're done. Okay, so let's have a look at this first one. So first thing, we've said the resultant force has changed, but we haven't said anything's happened to the mass. So we know the mass remains constant, which is going to be useful. So if mass remains constant, you can see that resultant force and acceleration are directly proportional to each other. And what that means is that if you double the force, you will double the acceleration of the object as well. Now you can try this out for yourself if you're not entirely convinced by this, and just put 20 in as your force and the same thing in for your mass, and you'll see that it comes out with double the acceleration. So you can try that out, but this is the logic I would use to explain it, and the first thing you need to identify is the mass is constant to make this logic work. Okay, so then next one. So now looking at section 2, which is the horizontal line section. Go back to it if you can't remember what it looks like. And what I'd like to do is explain what the resultant force is in section 2. Okay, so now you've had a chance to actually explain it, let's take a look. So, first thing is to recognize what the acceleration is during that section. So you can see that during a horizontal line section, speed is constant the whole time. And that means the gradient is 0 because whatever the y value is isn't changing. So the change in y is 0. And if acceleration is 0, we can plug that into our equation and see that resultant force would also be 0 if acceleration is 0. So those are the logic stages you need to answer that question. Okay, so we're going to move on to some different scenarios to explore what else Newton's second law, or F equals ma, tells us. So first off, we've got a car, and we can see on the diagram that it is traveling to the right because its velocity is to the right towards c. And what we want to do is identify the direction of the acceleration of the car shown, and we can see it's being caused to accelerate by a resultant force towards a. So again, I'd like to just write this down or think about it. Which direction do you think the acceleration is? Okay, so let's take a look because a lot of people tend to get this one wrong. What Newton's second law, or F equals ma, tells us is, yes, force and acceleration are directly proportional, but it also tells us about the direction of the acceleration. The acceleration always has to be parallel or in the same direction as the resultant force. So in this case, the resultant force is towards a, therefore the acceleration is towards a. A lot of people get distracted by the velocity. The direction of the velocity is not important in the slightest in terms of working out the direction of the acceleration, nor is how big the velocity is. The only thing that matters is what direction the resultant force is, so it's towards a. Okay, so next scenario, we've got a submarine and it's traveling at constant speed, and its engine is supplying a thrust force, so a forward force of 20,000 newtons. We want to determine the drag force, the one with a question mark you can see on the diagram. So again, have a go, see what you think it is, and then we'll go back to it. Okay, so the correct answer is the drag force must also be 20,000 newtons. So the key is the fact that a submarine is traveling at constant speed, and therefore that means acceleration is 0 if the speed is constant. And if the acceleration is 0, the resultant force must also be 0, which is why the drag force must be equal to 20,000, so the forward and backward forces cancel each other out, and you get left with a resultant force of 0. Okay, so we're going to have a look at a plane type scenario. So planes have a few different forces acting on them. In this nice simple model, we've got a forward thrust force, we've got a backward air resistance force, we've got a downward weight force, and we've got an upward lift force we're showing in red. So the aeroplane is accelerating at 10 meters per second squared upwards. Which of these statements is correct? Is lift force greater than weight force? Is lift force equal to weight force? Or is lift force less than weight force? So have a go, select which answer you think, and then have a think about why it is you're selecting that answer as well. That's just as important, and then I'll show you how I figured this out. Okay, so let's have a look. So First off, as we learned from the question with the sports car, if the acceleration is upwards, the resultant force must be upwards too. It doesn't matter about anything else. And if the resultant force is upwards, thrust force and air resistance must be balanced, so there's no acceleration right or left. And it also tells us the lift force must be greater than the weight force, so that makes the resultant force upwards. So that's why we need the lift force to be greater than the weight force. So now we're actually going to do some calculation with it. So we still got the same scenario. Acceleration is still 10 meters per second squared upwards. But we're now told that the weight force is 2.0 times 10 to the 6 newtons, and the mass of the aircraft is 2 times 10 to the 5 kilograms. And we want to calculate the lift force actually on the airplane. So again, pause the video, have a go, see if you can figure it out, and then we'll take a look at what the answer is. Okay, so let's put it in. So first of all, we have an equation to calculate the resultant force. That's what FA equals MA calculates, and I've just called the resultant force F for my working. So using M and A, we can figure out the resultant force, 2 times 10 to the 6. Now we also know the resultant force is the lift force minus the weight force because they act in opposite directions. So if we rearrange that, we know the lift force will be equal to the resultant force plus the weight force, which gives you a final answer of 4.0 times 10 to the 6 newtons. So that's the correct answer to the question. That's what we need it to be. Okay, so last question. When the aircraft is landing, it's moving forwards and downwards at constant speed. So then which of these scenarios is now correct? So again, have a look through the options and select your answer and have a think about why that's the answer, and then we will review that question. Okay, so let's pop the answer in. So first off, if speed is constant in both directions, that means acceleration is constant, and it's more specifically, acceleration is 0. So therefore, if acceleration is 0, resultant force is 0. So therefore, the forces must cancel each other out. So thrust force must be equal to air resistance, and lift force must be equal to weight force. So it doesn't matter that it's going forwards and downwards. The fact is a constant speed tells us lift force equals weight force, thrust force equals air resistance there. Okay, so that finishes this video looking at a few questions with Newton's second law, F equals ma. Have a look through the solutions to all of these questions. Make sure you are happy you can explain why each of these stages happen. And if you can, this is the time to stop watching this video as we're at an end. But if you can't, this is the time to go back and have a look through those questions. Make sure you can explain why everything is happening in the solutions. Okay, so thank you very much for taking the time to watch. If you have any questions, feel free to post and ask me, and I'll be more than happy to answer them for you. But thanks for taking the time to watch.